Hello and welcome to another mini lesson. In this lesson, we are going to talk about the transition from set theory to logic, which is our next unit. And we're going to talk a little bit about why we need logic and why we might want to think about logic and how we're going to think about logic in this class. All right. So we've already learned in our unit on set theory how to take statements in language like Belle is a cat and turn them into statements in abstracted language of set theory by saying things like Belle is a member of the set of things X such that X has this quality of being a cat, right? So this is our abstracted set theoretic language. We could also say Belle is gray, right? So Belle is a member of the set of things that are gray, right? So this is we've already done some abstraction here. But intuitively, we should be able to say something like Belle is a cat and Belle is gray. So we already talked about one way that we can do this in set theory by making the meaning have to do with the interactions between sets, right? But when we start talking about logic, we're going to do something a little bit different. We're essentially going to acknowledge the fact that this statement, Belle is a cat, in some given world that we've created in our mind, right? So some given distribution of what things are cats and what things are not cats, right? We should be able to say whether this is true or false. And we should be able to say whether this is true or false. Right? And then all that we have to do in order to figure out whether Belle is a cat and Belle is gray is true is to figure out the interaction between these different truth values. So what we're going to do is not only are we abstracting away from language, we're even abstracting away from our abstract statements to summarize things as one of these two meanings, true or false. And then we're going to integrate in what are called operators to do this. So let's look at how this works. So if we've got two statements here, a first statement, Belle is a cat, and a second statement, Belle is gray, we have options for whether those statements can be true or false, right? Either the first statement is true and the second statement is true, then the first and second statement will be true. Or if either of them is false, only one is false, then they'll both be false. Right, and of both of those will be false. Or they can both be false, and then Belle is a cat and Belle is gray is also false. We call this is approximately a truth table. And this is the kind of thing that we're going to be constructing, except that as we get deeper into logic, these operators are going to be more complicated than just and or whatever, right? So operators in logic are going to be different from our operators in human language because, for example, in human language we have and or no, we have and but, sorry, not or, and but. Right? These essentially do the same thing. Belle is a cat, but Belle is gray, still has the same truth table, right, as and, right? So what abstracting away from human language does is it unites all of these things in terms of their logic. And so our operator and, that looks like that, is going to include and but and all the other similar operators in English that just require that this be true and that be true. Both of them have to be true in order for the whole statement to be true. So this is the kind of thing that we're going to do in logic, but I thought I would orient you before we start delving into the details of it so that you have some sort of idea of what we're doing. Essentially, we're taking these sorts of statements and treating them as a big block that can only mean true or false. We're not worried about how we evaluate whether it's true or false. We're just talking about once we've blocked it off, what can we do with it? So that's what we're going to be doing in this logic unit, and I hope you enjoy.